All right. Okay. Hey, folks, let me share my screen. And thanks, Faisal, for the warm intro. We just get started. Please feel free to interrupt me at any time. I think we can keep this conversational. There's a bunch of points I want to get through, but I think it's more interesting always if people have questions and we're able to discuss. If it's a longer answer, we can take it offline or after the talk, right? So this talk is about bringing together the best of Amazon Aurora and Google Spanner. For a little bit of background, right? Like YugabyteDB is a distributed SQL database, and what that means is it brings together SQL and transactions, so keep the whole RDBMS, ACID compliance, all of that, retain all of that, but also enable people to be resilient to failures, to scale horizontally by adding more nodes, and to geographically distribute data, whether it's a multi-zone deployment, a multi-region deployment, synchronous, asynchronous, a lot of different options, right? So, but roughly distributed SQL lets you do this. I mean, some people call the space new SQL with this different number of phrases, but nevertheless, this is what it is in essence, right? With YugabyteDB, it's a fully open source project, as Faisal was saying. It's open sourced under Apache 2.0. You can think of it as effectively as open source as PostgreSQL. So all of the features, the so-called enterprise features, things like security and so on, everything is in the open source. And so YugabyteDB is a distributed SQL database with a focus at the design level on high performance, on being cloud native, which is so run it anywhere, Kubernetes, VMs, bare metal, and like open source, right? Like keep everything open source as a database. So first off, I want to say that in terms of like the topic title and the evolution, we started building Yugabyte in early 2016. So it's a little short of 5 years, just under 5 years that we've been doing this. And, you always look back at what the other databases did. I mean, one of the first questions that anybody building a database should answer is, why does the world need another database? Because there's so many databases, right? So to ourselves, we looked at what Google Spanner had. It's the database that came out first, right? The paper came out circa 2009, and the service came out 2011 or 12, like the cloud service. And Amazon Aurora, which was launched, I think, in 2015. So when we looked at the two, we found that there were interesting things that the two databases did that we would like to borrow from in order to build a database that makes application development for the cloud really simple, right? So if you're building a cloud native application, what kind of characteristics would you need? That's really what we were going after. So anyways, so in order to do this, we said we're going to decompose our database into two layers, a logical query layer, which is Aurora inspired, and a storage layer, which is underneath, which is Google Spanner inspired, right? So upper half is like Amazon Aurora, lower half is like Google Spanner. And what does that mean? Why do we need it? I think we'll go into some of those details. Just another aspect that I just mentioned up front is that the upper layer, which we talk about mostly SQL in this case, also supports a flavor of NoSQL, the YSQL or Apache Cassandra compatible API. And this itself is very similar to Amazon Aurora, which supports both PostgreSQL and MySQL, right? It's wire compatible and feature compatible with both. Okay, so what does Yugabyte do? If you take a single node Postgres, we're talking about the upper half or a high level view. A single node Postgres can be split into the query layer on top and the storage layer that deals with the single disk below, right? And what we do in Yugabyte is, in the first step, you can think of building this database in 3 steps. The first step is simply make that query layer stateless. So kind of change the way it interacts with the storage layer to go to a remote storage layer as well, right? And so this storage layer, as we talked about in the previous diagram, is inspired by Google Spanner and is called DocDB internally inside Yugabyte. And so now every node of the query layer can actually talk to any node of the storage layer, and the storage layer replicates data and behaves like Spanner, right? So that's what makes it highly available. But one downside of this approach is that you have to keep shifting all the data to the node that's handling the queries, right? So this could become really poor in performance if you keep shuffling around a lot of data. So step 2 is to start pushing down operations into the data layer. So we have this clean abstraction. We have the upper layer, which talks about how to handle queries, and the lower layer that talks about how to store data. But now we're saying, let's push more and more operations from the query layer down into the storage layer so that it can get handled closer and closer to data. So as an example, if you do a count star, or if you do find the max value of a column, you can either read all of the rows of the column into this node that's servicing it, or push down those operations like a max or a count star down, and including more complex operations over time to get them to execute closer to data, right? So that's kind of step 2. And step 3 is when you're trying to come up with a query plan, right? Like in terms of what are the sub-steps in order to satisfy what the end user is asking, you can just do what Postgres does and say, hey, let's take, like on a single node RDBMS, we take the size of tables and a variety of things into account. Now there's geographic location and the network cost, and how do you really optimize this for a distributed database scenario, right? So these were the roughly 3 steps. And in some sense, these 3 steps never end, right? Like, because you keep building the database. I mean, Oracle's still building the database after many, many years. So these steps never end. They just get refined and better with time, right? So these are the steps in the order in which we started them also, and hence also in the level to degree to which they are advanced and mature, right? Like, so the 3rd step is the least mature, and the 1st step is the most mature, right? So here we're going to talk about the journey of building YugabyteDB, like at a high level as it corresponds to these 3 steps. But we're mainly going to focus on some of the higher level concerns and primarily the step 1. We're not going to focus too much on steps 2 and 3 for now. Okay, so back when we started, we had to make a lot of decisions, right? So this really outlines some of the decisions and our thought process behind those decisions and how it turned out in retrospect and so on and so forth, right? So the first question we asked ourselves was this: there's Aurora, there's Spanner. They represent the most advanced databases in their own right in the cloud. Which one do we build, right? Do we build Aurora? Do we build Spanner? Of course, we gave away the answer at the beginning. It's a little bit of both, but nevertheless, right? So the first thing we realized is that Aurora's full compatibility is really a big boon to people, to enterprises, to use cases, right? Because, you know, all of the ecosystem, all of the apps they're building, they just work, right? Like, and Aurora is MySQL compatible and Postgres compatible, and it simply reuses the upper halves of these databases, and it kind of changes the way it stores stuff on disk to move to a distributed disk. Google Spanner, however, is horizontally scalable. It can geographically distribute data, and so it's got some really powerful like properties, but Aurora is more used than Spanner. And what that tells you is people care about the language and the API and the ecosystem a lot more than the features, because it's much quicker to build applications, right? And Postgres is absolutely on fire, right? Like, it's growing so fast. It's actually growing faster than MongoDB's. It's really popular all over the place, right? So that made it a little easy. Now, if you look at a head-to-head of what these databases have in terms of, you know, some features, on the query layer, we said Amazon Aurora reuses PostgreSQL and MySQL, whereas Google Spanner is its own flavor, which means it needs to build client drivers, ecosystem, everything anew. And it's, in terms of the SQL feature depth, right? It supports most of the Postgres and RDBMS features, Aurora does. So it's kind of comparable to any traditional RDBMS, like, you know, a SQL Server, a DB2, or Oracle. It's pretty feature rich. But if you look at Google Spanner, a lot of features are missing because it's starting with its own flavor of SQL. Like, for example, foreign keys were added very, very recently. And like, if you look at some of the more complex, like triggers and you know, partial indexes, these things start getting harder with Spanner. Both of them are fault tolerant. However, Spanner really shines when it comes to horizontal scalability. Just add nodes, you don't need to scale up. Aurora still needs to scale up in order to handle queries. And distributed transactions and global, like distributed transactions and synchronously stretched clusters across different regions, Spanner can do. Aurora does asynchronous replication, which is not to be underestimated, right? It's really useful in its own way. So with Yugabyte, we said that the top 2, the query layer and the feature depth, are extremely important for ecosystem support and adoption. And the rest of it is something we want to retain. So we said, here's the set that we wanted to go for. PostgreSQL compatible. In fact, it's Postgres and Apache Cassandra, but we'll deal with that later. We're talking mainly about SQL here. It's high degree of support for most of the Postgres features. So Yugabyte supports stored procedures, triggers, partial indexes, you know, a lot of extensions, some of the more complex features, and retains the Spanner characteristics of HA, horizontal scale, and distributed transactions, and does both synchronous and asynchronous replication. Right? It does both. So let's look into some of these, right? Like, so those are the bits we retain from Aurora. There are some bits we retained from Spanner, and some we got from both, right? And it's a big feature set, but, you know, if you're building a database after these guys, you better have something to really make it compelling, right? Okay. So after we decided on the feature set and we decided that Postgres is it, and that's what we're going for, the question was, do we reuse PostgreSQL or do we rewrite PostgreSQL? PostgreSQL is a pretty large and mature code base, right? So we said like, okay, let's actually rewrite it. It's going to be much easier to rewrite it because, you know, how complicated can it be? Then we said, okay, we actually went about rewriting it for about 5 months or 6 months. And we said, okay, we're going to go with this strategy. We're going to support some basic data types. And then we're going to support like some schema. And we'll support like the basic operations of listing tables, dropping, creating tables. And then we're off to our races to add other stuff, right? So we said, okay, let's do this basic command /d in order to list tables. Like, I don't know, somehow we should have done it on day one, but we did it 4 months after we had a bunch of stuff built. Well, it turns out that is really how the query looks. If you do a /d, that's what it really issues to the database. Now, if you look really closely, it has a case statement, it has a select, it has aliasing, it has like, you know, built-in functions like pgcatalog.get some user by something. It has a left join, it has where clauses, it has order by. Like, if you support all of this, you pretty much are supporting most of your database anyway, right? So we said, okay, this is not going to really work. Let's rework this strategy. And we said, like, you know, we're going to reuse Postgres, and that has let us really support a very high degree of features. And of course, /d works in Yugabyte now, but, you know, so does a lot of other stuff. Okay, so if you look at the overall feature set that is needed, and like a lot of people will tell you in this previous slide that, hey, who really uses triggers, who really uses stored procedures, or like, you know, or so on and so forth, right? It's true that a lot of things we interact with directly as frameworks will not use a number of these things, but a number of these things are used by those frameworks. So if you really want any framework to simply work on the database, you pretty much need a wide array of support, right? Like, even with all of this, we still find some features missing that we would have to support over time, and we are adding those, right? So the point is, it's a very wide set. People end up using these RDBMSs in really novel and interesting ways, and they use many of these advanced features. Okay, so our point was, if you're rebuilding this, it's 30 years of development on Postgres versus, like, you know, the 4 or 5 years we've been around. Even if you speed things up, you can only do so for so much, right? You can't do it all the way. So we wouldn't be able to support this in a timely manner. So what did we do? Like we talked about in the first slide, this is the a slightly more drill down view of Postgres. We said we wanted to reuse the Postgres upper half. So literally what the query hits to how it's, you know, planned, executed, rewritten, optimized, all of that is mostly the same. We replaced the lower half with our own table store. So it kind of looks like a row store to Postgres, and it interacts with any node underneath. And we wrote our own bridge layer. It's called the YB gate, or the gateway to YugabyteDB. And we made a bunch of changes to the planner, the executor, the optimizer, keeping the postmaster and the entry point the same for authentication and authorization. And so that really has allowed us to convert the upper half of Postgres into what looks like a stateless upper half, right? So at this point, every node in a YugabyteDB cluster has an upper portion. It's a part of the same process, but the upper portion, which is stateless PostgreSQL, and the lower portion, which is a distributed spanner-like store. And so your app can connect to any node, right? And if you lose a node, you're completely fine because you can connect to another one. The lower portion is fault tolerant and can do failovers pretty quickly. The upper portion is stateless, and so you just simply connect to another node if your node that you connected to failed, and you'll be able to continue performing reads and writes and so on. Okay, so now we've gotten through two pieces. We knew.
Karthik, a quick question.
Yes.
So you mentioned this concept of going from stateful to, I guess, stateless in the Postgres. What exactly did that entail? What did you have to do?
Oh man, that's a very loaded question.
Yeah, give us maybe a short version of it.
Okay, so I'll give you a couple of examples, a couple of big examples. Okay? So the first problem in PostgreSQL is that, so Postgres has this notion of how it stores data in blocks on disk, and it can actually use the pointer to those blocks in order to store it and locate data, right? In Yugabyte, the blocks will not be on disk, it'll be on a remote node. So we'd have to change how that works, for starters. Secondly, the system catalog of Postgres is just a file that's generated underneath, and it's easy enough to do so, but it's not highly available and it's not distributed and fault tolerant. And that's something we had to fix, right? Now, the strategy to make the user tables distributed is completely a different code path from the path to making the system tables highly available, because they just follow completely different code paths in Postgres. So that's another huge piece of work that we had to do. Third thing is Postgres makes a lot of lookups to its like metadata, which is all in memory on the same node, right? In case of Yugabyte, all of these start translating to remote RPCs. So, I mean, it's not a good database if, for example, you do a simple query and it's going to do 50 remote lookups only to look up 50 different small pieces of metadata to another remote node, because it needs to figure out the system catalog pieces to get joined, right? So now we had to distribute the system catalog all over the place and get that replicated, and we had to have a way of ensuring consistency across. So, I mean, these are some examples, but we had to do a lot more of these in order to make them, to make it really work. But the trick was, I mean, so the bottom line is there is no code path in PostgreSQL. There are 3 code paths in Postgres that you can take. You can go after the native code path, which is all the way, or 2 code paths for the user tables. You can go after the native code path, which works with all of these pointers and all of that in memory. Or there's a foreign data wrapper code path, which is limited in what all it can expose. So Yugabyte could not be added as a foreign data wrapper. So we had to create a 3rd code path, which hybridizes these 2 and gives you the best of the both worlds, right? So it was really like building a whole lower half of Postgres from scratch, while retaining and playing nice with the upper half. So hopefully that gives you a flavor.
Yeah, so what I get a sense of is that by stateless here, you meant being able to decouple this from the representation of the lower half.
Exactly.
From storage layer. So storage independence is the storage layer. Okay,
yes.
Got it.
So not stateless in the sense you can point it against anything, any remote storage and run it. That's not the point. Yes, you're right. So it is decoupled from the local store where it was totally tied, right? All the state was assumed to be on the local disk. Now it's not.
And the challenge was in making the scale at the same time, like being able to
performance and scale. Yes, performance, scale, correct. All of these were challenges, right? So. Okay, so the next major decision, now that we were reusing the upper half of Postgres and we were doing a blend of Aurora and Spanner, was how do we basically ensure consistency of data, right? So we said we're going to use Raft for single row linearizability, which is if you write, we talked about Postgres, we using it as a row store. How do you ensure that this row is going to be consistent and replicated and fault tolerant across nodes, right? That problem. So if you think about what Yugabyte does, it automatically partitions tables. So you have a table like the one you see on the left, and it automatically gets split into a group of rows underneath, and each row is called a tablet, and this happens automatically without you having to worry about it. It can be dynamically split, it can be statically split, you have control over how it's split, but the point is it's split transparently, right? So the replication is done at a shard or a tablet level, right? Like, so each tablet, like you now split a table into a lot of tablets, you pick up one tablet and you replicate the data of that tablet across multiple nodes, right? Now, in order to replicate it, like if you have 3-way replication, you see this here, you have for that tablet, you have peers 1, 2, and 3 that live on 3 different nodes. They could be across zones, regions, whatever it is, but they're on 3 different fault domains. In this case, they're nodes, right? Now, the way we decided to go in order to maintain consistency, you needed some kind of consensus protocol in order to ensure that even in the case of failures, all these nodes agree on the value of these tablets. And we used Raft for that, right? So the Raft algorithm works by electing a leader, for those of you that are familiar with it, but I'm just describing it at a high level. There's a lot more complexity to it, but at a high level, it elects a leader. All your reads and writes are processed by the leader. And if you're doing a write, for example, the Raft reader gets it and it replicates to all the 3 copies. It waits for itself and one other copy, so which is a majority, to persist data and acknowledge. And then it responds saying, hey, this is now replicated, like very high level. The problem with this approach, and on the read path, right, it does something similar. You get a read to the leader. It now has to send a heartbeat to each of its replicas and hear back from a majority. Only then it can establish that it is a leader. And then it's going to respond with the value, right? The problem here is that it's really slow being a geo-distributed database. So imagine if you had like 3 copies in 3 different corners of the country, and you did a read and it's waiting for all these heartbeats to come back. And so your minimum latency is like 50 milliseconds, right? That's the fastest your database can go. It's not a high performance database. So we said we really had to solve this problem of doing consensus-based reads. So we decided to implement leader leases, right? So what that means is every leader as a part of the Raft protocol itself, and then the Raft paper talks about leader leases, but it's just mentioned in a couple of lines, right? So the reality is it's actually a little more complicated and nuanced to implement. Anyways, in this diagram, you assume that node B wins the leadership initially in the first part, as you can see here, and it replicates data into its other guys, which says, I will own the leadership for a period of time. Nobody else can step up to be that leader for that period of time, right? So, and this is renewed through the Raft heartbeats. Every time there's a heartbeat, it says like for 2 more seconds, I'm the leader, and nobody else can like question or assume leadership. And so we were able to serve the data directly from the leader because you have the guarantee that nobody else can step up as the leader in that window of time and accept writes, and you'll be serving stale reads or writes. Right? So this is what this diagram kind of puts together. Okay, so the reads now are handled only by the leader, and it uses leader leases for performance. And if you think about Raft, there's a lot of other performance enhancements, like starting from the fact that Raft only talks about a write-ahead log, but your database is not just a write-ahead log. You need it all in a data file. So you need to somehow checkpoint the state across the write-ahead log and the data file and make sure that is consistent across nodes. That's a simple one. But there's other things for performance and safety, like, for example, using monotonic clock instead of system clock, because like one of the things we try to do for single row linearizability is to depend on time windows or delta t instead of absolute time, or like, so that will change your it will change what you're doing with clock skew to instead track clock drift, right? So when you're replicating data for leader leases, we always replicate only the time interval for which you need the leader to be the actual leader to have a lease. So let's say it's 2 seconds, and everybody else computes that 2 seconds from the monotonic clock, the hardware clock, not the software clock, which can get adjusted by NTP, right? So this is one of the things that makes Yugabyte very robust to clock skew and clock jumps and so on. Another one is that Raft talks about every update, but we do a batched update. So we grab a bunch of updates and we order so we grab a bunch of values and we put an order inside a single Raft round trip. So there's an ordering inside like the Raft log for every entry, and you could have a group of entries. And that way you'd actually get much better throughput and performance and so on. Right? So there's a number of others, but again, just to give you a flavor. Right? Okay, so we now have Raft for single row linearizability, and having decided all the other parts of the system. So the next decision was, how do you do per node storage, right? What do you choose for that? And like, do we start with something known like RocksDB? Do we reuse it as a black box? Do we modify it? Do we, like, what exactly did we want to do? Well, the key realization, I think even before I think probably these slides should be reordered, but anyways, the point here is we use a heavily modified RocksDB because we decided that we want to build a key to document store, right? If you want to build a multi-API access pattern on top, we decided the best bet was to keep it document-oriented at the bottom and really optimize the access paths from each of the API layers above. So DocDB changes RocksDB's internals to make it understand a group of rows instead of just a group of key values, instead of just a key value. So you now have the notion of a document with attributes and sub-attributes and ability to fine-grain, read, write, update attributes, and so on. And we took out the write-ahead log of the RocksDB because it's not useful. We have a Raft log on top, which maintains consistency and what we'd like to drive through. And the minute you take out the write-ahead log, you have to also pull out the MVCC, the multi-version concurrency control, which decides when you can expose a read to the world, right? So we said we're taking out all of that stuff. And once you've taken out the log and the MVCC and changed the file format and the seek and everything to make it a document, it pretty much was a heavily modified RocksDB at that point. So that decision was, let's start with RocksDB, but let's unify it into the product tightly, couple it. And the storage layer of DocDB, like the RocksDB also had to get heavily improved for the performance paths that we were taking. Like the way we do it is you'd have multiple tablets or shards on a single node. So we needed to make multiple RocksDBs running on a single node kind of share and pool their resources. So that's like the global mem store limit that can get shared across, because you can have one table which has a lot of reads, another table which has a lot of writes. So that kind of stuff. Similarly, ability to have a global block cache and also make it scan resistant, which we added into RocksDB. So you have like high throughput lookups of repeated keys with a full scan of the table, and the full scan shouldn't wipe out your high quality cache where your multi-hit data is actually preserved. Similarly, sharding and splitting Bloom filters and indexes so that your unit of I/O is actually pretty small. Multi-compaction queues, a bunch of other things, right? Ability to load balance across multiple disks on a node. So a number of other enhancements into RocksDB to support our specific usage pattern. All right, so this is how it gets encoded underneath. Again, it's a very high-level logical implementation, but you have a document, a subkey, and you have attributes and values. It can be nested. It all gets flattened out and written as multiple keys logically. I mean, physically, it gets this prefix compression and a number of other things, but logically, it gets flattened out into document attribute values all the way at the lowest level, with the notion of a collection, right? Like we're able to define when a whole collection gets reset or something. That's the init marker, right? You can actually say, I've changed my whole collection and don't seek below that. And this goes into some more details of how the actual row and value is encoded, right? So you have a document key and you have the subkeys. So the entire primary key is serialized along with the hybrid timestamp of the update that's needed for multi-version concurrency control. And it points to a value. The values have types. In the Postgres case, the values are serialized as per the Postgres serialization format. In the YSQL or the Apache Cassandra compatible case, we serialize it in that wire format so that whatever you return can get quickly sent all the way back without having to deserialize a number of times. Okay, so that was the storage layer. Now, we talked about a lot of things, but now if you issue a read that cuts across nodes, right, like a long-running scan or a multi-tablet scan, right? How do you synchronize? So, Google Spanner does this famously by using atomic clocks, but the rest of us don't really have an atomic clock. So the real problem here, to give you a motivation, is if you're doing a distributed transaction, you have updates that can belong to different shards, and the shards belong to different nodes, right? So the real update looks like you are making updates across Raft groups, right? So you're just making these updates, each of which is atomic and linearizable and all of these good properties, but these happen across, and all of these updates should be atomic, not every single sub-operation be atomic, right? So they need to have the same time, and that means that the nodes need to agree on time. So you can write to 4 or 5 different nodes, and when you flip it, everybody should agree that this is the timestamp that I can serve, and there will be no update that happens before this timestamp because you want a repeatable read database, right? You want the properties of, you don't want your data changing under you. So your best bet is to use the simplest approach is to use a physical clock. But if you're using physical clocks, you need an atomic clock, right? Because you want something that's highly available, globally synchronized with tight error bounds and so on, which is really what true time is. And most of the people would say, they don't really have these type of atomic clocks lying around, and the clocks that they do have aren't really synchronized. So that puts that thing up. So we decided to opt for hybrid logical clocks, where you combine a physical clock with NTP. And by the way, what's wrong with NTP or using physical clocks, right? Your max bound or the tight bound that we talked about, the upper limit of the bound can go easily as high as 150 to 200 milliseconds, right? So imagine a database which says, I'm like giving you all these great properties, except the minimum transaction latency, minimum latency is 150 to 200 milliseconds. Right? It's not going to be a very useful database. So we said we're going to use the physical clock and NTP to do synchronization of time coarsely, but within that, we're going to use causality in order to determine if there is if there are failures that we need to track, or if there are conflicts we need to track, or if there's something we need to restart and so on. Right? So in the majority of the case, there will be no conflicts. Everything will go through fine. In the minority of the case where there are conflicts and they are causal, we are able to detect them using these causal chains. In a real minority of situations, you could have scenarios where you just don't know because you haven't established a causal chain. In that case, you'll have to figure out that will be treated as a conflict, right? And so, and each of the nodes exchanges and updates the hybrid logical clock on every exchange, be it a Raft heartbeat, a leader election, data replication, API, anybody communicating with anybody will exchange clocks. A node with a hybrid logical clock will compare any incoming hybrid time. If the physical component of the incoming guy is higher, it updates to the higher time. If the physical component of the incoming guy is lower, it just sticks to its own physical time. So the node with the fastest clock kind of brings everybody's time up over time. I mean, that's really how the system works. Okay, so the next step was distributed transactions, right? That's pretty critical to most of these relational workloads. So how do you do that? Well, distributed transactions in Yugabyte are very similar to Google Spanner, based on a two-phase commit, but uses hybrid logical clocks. That's because it gives you far better scalability, and it's really good for multi-region deployments, right? You want distributed time synchronization so that all operations happening in one region can just synchronize in that region, as opposed to going across the wire to a remote region in order to fetch a timestamp. And our assumptions when we made this decision are that over time, global deployments will get very popular. So you don't want to have a single clock centrally sitting somewhere and everybody go there to fetch time. And the clock synchronization in clouds will get better over time. And sure enough, it's playing out that way, because Amazon now has a time sync service, as does Azure, in response to Google's true time. And so like over time, this will just get better and better to a point where this just becomes a staple in many clouds, right? And we really didn't want any hardware-based things, but still wanted to afford the ability to use a hardware-based clock if one is available. Right? So Yugabyte can use an NTP-like synchronization system, NTP or Crony, even if it is like GPS-based. But if not, we can just make do with regular NTP and a max clock skew bound. Okay, the second part was it's a fully decentralized architecture, no single point of failure. The transaction itself is maintained in a distributed replicated table, and that's called the transaction status table. Every incoming transaction is recorded in the system if it is a distributed transaction. If it is a single row transaction, it goes straight up and makes the update. It's called the fast path versus the generalized distributed path. A transaction can have three states: pending, committed, and aborted. And you can only serve reads for committed transactions. If they're aborted, you simply ignore them. If they're pending, you have to go and figure out if it's a conflict or a potential conflict, or you have to run conflict resolution rules, right? The isolation levels that Yugabyte supports are serializable and snapshot. Serializable obviously maps to Postgres is serializable. Snapshot isolation maps to everything else. So repeatable read, read committed, read uncommitted, everything maps to snapshot. We don't do like really read uncommitted and all of these things because it feels a little theoretical and not as practically useful, right? And for transactional workloads, we're talking about systems of record. The read-only transactions obviously use MVCC and are, for the large part, lock-free, right? Like they can have contention, but they can have conflicts, but they're lock-free. So let's go through a simple update path just to take a look, right? So let's say you have a tablet that, and the query can go to any node we say, right? So let's say the node one, the tablet server one is the one that's handling the transaction, and tablet server two is the tablet server that has the piece of data of the status tablet, right? So you're updating two keys, K1 and K2. You first write into a status tablet saying, hey, here's the transaction ID, and this is what it's trying to do. And then we go and write what are called provisional writes. They kind of serve as persisted locks or persisted locks. They're just called provisional writes. We write the values, but we say they're a part of a transaction that's in progress. So that means anybody coming to read them would first have to go to the status table to see what the status is. And we then talked about if it's pending or aborted or committed. If you're able to successfully get all of these provisional writes, then you can go ahead and flip the transaction to committed. The timestamp at which it gets flipped to committed is the timestamp of the transaction. That's when the transaction gets committed. If you don't get all of the provisional rights because somebody else has a conflict or something fails, then the transaction gets flipped to aborted, right? At that point, you're just done. You don't have to, you can ignore the transaction. Then two things happen. Step 5 is respond to the client, but step 6 is that perennially after this, every read coming here would have to go back to the transaction status tablet, see that it's committed, and then serve it as of the timestamp. To prevent that, we flush the value down to these tablets so that over time they get consistent and they can directly serve the data. So for a short period after the transaction, there are 2 hops, and pretty soon after that, it gets resolved to a single hop. Okay, so.
So sorry, Karthik, just a quick question about the previous slide.
Yeah.
So I'm assuming that when picking a timestamp or a logical clock reading for a transaction, that you would need to make it ordered according to the conflicts with the concurrent transactions. Where is that happening in this diagram?
So the transaction conflict is really detected as a contract between the transaction manager and the tablet or the tablet server and the tablet service. So the transaction manager gives enough context to whatever, like as a remote RPC call, to the actual tablet service that's executing the operation to say, this is what I'm trying to do. This is the transaction I'm a part of. This is the isolation level I'm running in, and so on and so forth, right? So when the tablet server is actually trying to perform this provisional, right, it goes and checks that, is this going to really result in a conflict based on both the committed updates as well as the pending updates I have in my queue. It looks at all of that, right? So if it finds that there is going to be a conflict, then it tells the guy back that, hey, there is a conflict. You can now decide. You would be conflicting with transaction ID Y, your transaction ID X, you'd be conflicting with transaction ID Y. What do you want to do? Do you want to abort? Does the other guy want to abort? And so then the transaction priorities come in and a bunch of other things happen. Right? So at this point, note that Yugabyte is optimistic in its concurrency control, which means one of the two transactions will get aborted. But we are working on pessimistic, where presumably at that point, this transaction can go into a wait queue, and then you can figure out your deadlock detection. All of that gets built around, right? But that's not done. That's still in the early design phase, right? But anyways, the detection is happening between the transaction manager and the tablet server. Like, it's between that at each provisional write. Of course, these will happen in as much parallel as possible. But sometimes you can only do it in sequence if the client keeps giving you one operation at a time and so on.
I see. Thank you.
Hey, Karthik, this is Keshav from Couchbase.
Yeah.
How do you maintain the consistency or do consistent reads from indexes, right? Here it's a simple set of setting two keys to values, but if you have a where clause, you have to qualify them. So how do you do that?
Yeah, so the where clause, so we are right now updating two tablets, right? They belong to the same table, but they could belong to two different tables. That's fine. The process is the same, right? Because so you can now, so think of key equals value, key one equals value one. Think of key two equals value two as value one equals key one in a separate table, okay? So think of having two separate internal tables, and you're making a transactional update across these two tables. Now, when you have an index-based read that comes in, it's the Postgres or the query layers, the optimizer and query planner that decides, hey, this is an index. I think I'm better off going to the index table. And it'll then go to, say, the key two equals value two, which is, in this case, an index table, which has value one equals key one, right? So it goes to that table to read, and it'll see that, hey, I have a provisional record here. And do I want to include this provisional record, or do I fail, or do I restart something, right? At that point, it'll detect there's a conflict between the read and the write, and so the tablet server is going to tell the transaction manager, you need to abort and restart, as one example. So this guy just restarts, and the minute it restarts, you've already established a causal order, right? You know that anything starting after that provisional write has to happen after. There's no ambiguity in time and so on. Does that make sense?
Yeah, I mean, so do you include the true time within the index entry to see if it qualifies, or
absolutely. So this is all has the transaction ID while the transaction is running, so you can go figure out the hybrid time. But if you remember from my old slide on the RocksDB format, the docdb storage format, if you remember this slide, this is the document update hybrid time. So this is the timestamp that's included with the key itself.
Okay, thank you.
Sure. Good questions, by the way. Okay, so the next decision that we had to do was the big one of actually, do we want to support asynchronous replication or not, right? It turns out that even if you can do synchronous replication and read replicas, right? Read replicas are, like portions of the cluster that can only do reads, and you don't need schema synchronization. They cannot do any writes. So we had those two already. But it turned out that a large portion of the world, thanks to Oracle, Golden Gate, and the traditional RDBMS replication, actually wanted asynchronous, and it made sense in a lot of scenarios. Like, I'll give you a real example. Let's say you have a retailer that wants to have a checkout, they want to build a checkout service, and let's say they decided to put one cluster of Yugabyte or whatever database in the East Coast and another one in the West Coast. The way they do this is they'd say they partition their user base into people in the east half of the country and people in the west half of the country. Everybody in the west half transacts against the West Coast database, and the one in the east does against them, right? But let's say the East Coast fails for whatever reason. They want everything to just work on the other side, but they don't want to pay the penalty of every operation and the right path going east to west. So they don't want to incur that penalty. So in this case, having asynchronous bidirectional replication from east to west, west to east really makes it super interesting, right? So that's one of the things that we decided we would build in. And this makes it complicated when you have all of these draft groups and distributed transactions and provisional rights and all of that stuff going on, right? So that's really the motivation. X cluster or cross cluster replication allows two or more completely decoupled YugabyteDB clusters to consume the data change from each other, right? And we make the assumption that they have the same schema. I mean, this is not very different from how you would expect to do it in a traditional RDBMS with asynchronous replication. This same feature also enables generalized change data capture, where you can get a stream of updates from the database and put it into any system, like, you know, like a search system like Elasticsearch or a Kafka or whatever it is to do other things, right? Some of the guarantees we wanted to build here, and this was like brand new areas that we had to kind of think through, because, you know, there's really no other database that does horizontally scalable transactional along with asynchronous replication cross cluster, right? So we said we would do in-order delivery of updates to a row, and therefore non-distributed transactions will be fine as it is. You don't have the ordering of updates that are being delivered to the other side that are guaranteed across tablets, right? And this is a good enough trade-off in order to get data for a high-performance distributed system. So what this means is, if you're doing key 1 on node 1 and key 2 on node 2 in that order, your replica stream could have key 2 followed by key 1, as long as these are not transactional. So if you're doing a transactional update of key 1 and key 2, it'll be atomically applied, and that's the intent. But if you do 2 independent operations, you could get out-of-order delivery across nodes. But within a single tablet or shard, you'll get in-order delivery. And every change will be delivered at least once, so nothing is left out. It'll be monotonic updates. So that means if you send an update, you cannot send an older update. So it's got to follow like the tight raft ordering. So if you know up to where you have sent the updates in the raft log, and you can only continue from after that. And periodically send no-op events to know when the other cluster is actually caught up and up to what point it has caught up and so on, right? So you know that your RPO, so to speak, or your recovery point objective, and as to when you are really, how much data you'd lose if you lost the source cluster. Okay, so now comes the interesting bit, right? So now you could have transactions or updates on both sides. How do you do conflict resolution? In the simplest example, I do x equals 1 on the cluster on the left, I do x equals 2 at the same time on the cluster on the right. So the way we do this right now is just simple last writer wins, because, you know, between consistency and availability, you really have to give up on something. So we just assign a consistent write as of each of the clusters, and it just depends on the natural clock drift between the clock skew between these two clusters. The one that has the higher timestamp, irrespective of the order in which these happen, will just be the one that wins, and the two clusters will write to send to each other, and they'll converge on that. Right? Now you could have, for example, a unique constraint. So you could say that, you know, you could only set x to one value. So when you say x equals 1, you say there's only one value in the entire table that can have 1, and you could now already have y. You could have y equals 2, x equals 1, y equals 2. You could set x equals 1 and y and x equals 2 at the same time on the two clusters. They both will accept it. When it replicates across, you could now be violating the constraint, because x could be equal to 2 and so could y, right? In this case, your thing just fails. The transaction apply fails, and this is something that, you know, the users building these applications would have to keep in mind, that things like unique constraints and some of these things would just not apply. So yeah, and these updates will be dropped. We did think about exposing conflict resolution to users, but decided it's far too complicated. So we'll probably revisit that at a later point. I mean, it's definitely happened that some things we thought were complicated were exactly what the users wanted, but right now we're not exposing that. We're just doing a last writer wins automatic handling. And the last piece is about distributed transaction atomicity. So when you have multi-row updates on one side, what happens, right? So the updates that replicate to the other side of the various sub-operations inside a transaction go to the other cluster, the target cluster, in a waiting to commit state. Until all of the updates for a transaction land, they're completely in a waiting to commit state. Once everything has landed, it flips to committed, and then you can start reading, right? So it's kind of like the same two-phase commit or the tracking through a status table trick that we use. So the status table, instead of it being committed, is going to be in a waiting to commit state. And once all of the pieces land, the waiting to commit then flips to commit. Some of these features are in progress, like specifically around the last bit around transactional atomicity. We issue the same timestamp, but the sub operations today are not atomic. That's something that we're working on, and a couple of other things in here. But roughly, this is the design that we're going with, and the way we're enabling this feature. Right? Yeah, this is going into a little bit more design. I'm going to skip some of these slides, but of course, happy to talk to people if they're interested. I think I'll just tell a couple of interesting things that come along the way, right? One of the interesting problems is bootstrapping, which is if you already have a cluster that has a bunch of data, how do you populate the other side? Because you wouldn't have all the write-ahead logs to send, right? So in this case, we do what is called a bootstrapping. So Yugabyte has the ability to do a transactional distributed snapshot, right? So we do a complete distributed snapshot. The same thing is used to, for example, do a distributed backup of the database. And after the snapshot, we start collecting the wall logs, the write-ahead, the journal logs on each of the tablets. The snapshot is transferred to the destination, and then the logs are replayed in order and so on and so forth. Right, so that was the trick. Yeah, just note that you could have different set of nodes on the two sides, like you could have a bunch of different things. There's also a lot of optimizations that we do in order to, try to not like scatter the replica streams. Like if there's a tablet on one side and we can establish a one-to-one correspondence with a tablet on the other side, and we try to pair those two so that you don't have to hit one node and then send the data to another node to get applied and so on. We try to minimize those, but obviously tablets can split, tablets can move. So this is a best effort, and it keeps following and chasing the data rather than, it's not a guarantee, it's a best effort. Our bidirectional is simply two unidirectional streams going in opposite directions with protection for this echo chamber problem where you send data, the other guy sends you back the same data, and you keep sending back the same data back and forth infinitely, right? So we just protect that by tagging it to make sure you know where the data is from. There's a so now next immediate problem or feature is like you could have one source cluster feeding multiple destination clusters. So each of these streams or destination clusters are stored in the system catalog, and you have a stream ID, and every tablet has its checkpoint for the stream. So a cluster that gets partitioned for a while can come back and request from the source cluster, hey, this is my ID, where do I leave off, and pick it up exactly from there. Right? So it's able to do handle partitions that way. Yeah, I think that's all I had. I just wanted to call out, like, we're a completely open source database, so we really appreciate all of your support. I think these are old numbers. The numbers are different at this point, but we have a number of users using us for, like, reasonably mission critical use cases, including a bunch of the stuff we're talking about, like including, transactions and indexes and, asynchronous replication and all of this in production. So like at pretty high workloads. I think there was one question that talking to probably Mike or somebody about how big does everybody need scale, right? Like these are even smaller companies that have pretty big scale, like Plume, for instance, is like last year's numbers were 27 to 30 billion operations a day. I think this year they're well north of 75 billion operations a day on a Yugabyte cluster. So with Amazon zone failing in the EU region, and so it's all real, right? Like it's no longer theoretical, at least like in the more recent couple of years. If you like what you heard, like, give us a star on GitHub, join our community on Slack, always interesting conversations. I mean, I'd love to take questions, but if you don't get to everything, you can always ask on Slack. We're always interacting.
Great. Thank you so much, Karthik. Very interesting talk. I know that everyone really enjoyed it. So I think we have time for questions. If anyone would like to chime in, either write in chat and I can read it out loud or just speak up.
So Karthik, very interesting talk. This is Sharad.
Yeah.
Very nice. I wonder if you have some performance numbers as to how well your system performs.
Yeah, absolutely. So
you can share that with us. So it'll be interesting to see what your performance looks like.
Yeah, absolutely. So performance is a wide spectrum. I'll give you some characterization so it gives you an idea. In a public cloud on a multi-zone single region setup or even a single zone setup, something like that, right, where the performance could be really high, If you're doing single key updates, right, like just single row updates, you could see about 1 to 2 milliseconds of write latency. It's a three-way replication. And you could see sub 1 millisecond latency for reads, right? I'm talking about simple primary key, no indexes, nothing. Right? Then you go to indexes, and now you have distributed transaction overhead and something. So this now jumps, it depends on how many indexes you have. If you have a single index, you could have about 3x the latency, because we talked about a number of RPCs that are needed in multi-table operation like tracking. But in reality, we try to do a number of things to optimize it, but it's about 3x worse in terms of, so 3x the latency, 1/3 the throughput, right? That's roughly what you get with one index, right? So that's that. In terms of batch operations, we're able to be pretty efficient, like obviously, and it's just a spectrum from there, right? So it just gives you an idea of the most bare bones all the way to more complicated things. Hopefully that gave you a ballpark, but
yeah,
there's different ways to measure. There's TPCC and there's YCSB. It's like more and more complex things as you get into transactions, multi-operation transaction joins. So they just like just different ways to measure it. So and we're not optimized for every query path, right? Like, so we're still in the early stages of optimizing like some of the SQL code paths. There's so many of them. More questions, folks?
Hey, Karthik, this is Chen Li. Can you hear me?
Yeah.
Yeah, a non-technical question. What is the business model? Are you giving a license, provide support, and how do you compete with other existing solutions?
Yeah, so that's a great question. So the database itself is fully open source, and it's not just support that we do other things. So we actually have I just want to open, yeah. So we actually have a different product that, I mean, I'm happy to do a quick demo, or I just want to go after one slide that I wanted to show. We actually have a product that does DBaaS orchestration as software. And another one, which is a fully cloud-based service. So our models are, we help people go from, it's like, these are our three things. The database itself is core and it's fully open source. The platform gives you enterprise support and orchestration that helps you in turnkey manner to install this on your own account in your public cloud. And it does things like, nightly back, if you're on AWS, it will do instance provisioning, create machines, create security groups, install software, manage the lifecycle of machines, change machine type, node upgrades, security patching, nightly backups, health and metrics. So it does all of this in software. So it helps you manage and run a database as a service, private database as a service. And we have a Yugabyte Cloud, which is still in very early phase. It's still in beta, but it'll be an endpoint that you manage. Right? So it will be these are the three things that we, or the two things that we monetize on. The primary database is all that we talked about today. So hopefully that answered your question, but I can show you roughly
You mean the first one, the first component on the left, that's open source. So that one, you don't sell license for that code base.
Because it's just open, right? It's like,
yeah. The second one, is closed source. You sell services licenses.
Yes, we're subscription based on the number of cores of the database that people manage under this instance. So it's really, because the more you manage, the more there's effort on our side. It's not the size of data; it's the number of cores, as you'd expect.
And this is a closed source.
This is the source available, so the source is in the open, but it is closed in terms of license. So it's a commercial license.
Okay.
And so like
that's your main kind of a revenue currently.
That's our main revenue currently. The cloud is still very early. It's in beta. It's something that we will release and have sometime next year. But just to give you a flavor of what we're talking about, so this is for example, a full-blown DBaaS that we have as an installation for ourselves, but anybody can install it for themselves. Our customers can. And you can go in there and you can kind of configure this to run on any public cloud. So this is all regions of AWS, all regions of GCP. So if you install it, you put in your credentials for the cloud, and this thing can spin up machines and do nightly backups and all of that stuff. So you just can create a cluster by saying, hey, I want a cluster in AWS, and I want this in whatever region of the world. And you can then say, just hit create and it'll create the machines for you and so on and so forth.
And the clients, they pay for the machines. That's their account.
The entire thing is in their account, including this console. Everything runs in their account. And so they pay for the machines, and we only charge for the cores of Yugabyte that they get service for, because obviously we will be 24/7 support on these and a number of other things.
Okay. And if you compare your product with other services like a Spanner, what makes your services more attractive? Price or features? Like you had a very nice table to show the pros and cons of the Amazon and Google services. Because you have all the check marks. That's your main advantage.
Yes, so that's the advantage on the database side, which is the primary advantage, I'd say. Like, so people wanting to use Yugabyte should primarily see the value of the database more than anything else, because it really simplifies application building, right? If you go to a Google Spanner and you have a workload that's single row, but large data, you'd have to use like a big table, or you have to use something else, right? And if you ever are going to a different cloud like Amazon for either a different app or because you want to move your app or a portion of your app, you have to re-architect your application, right? And there are many cases when you have hybrid deployment, you have your own data centers and you want to put a little bit of data in the cloud, synchronous or asynchronous, right? So these are places where we really help. I think the other place obviously is true to any open source database where you may have some workloads that really you don't want to run in the cloud. Maybe these are test instances or dev instances or staging instances. So you can run those in-house like at a lower price point, and you don't need the full-blown management. So there's some of those advantages as well. But I'd say those are all secondary. The primary advantage is the developer velocity that we bring with this, right? So it's literally like, so if I go into, say, a test cluster here, this is a geographically distributed cluster that you can create simply by clicking on a few things here. Like you just click these three things, you say, these are the nodes, you put some flags, you say this, and then you say create, right? And it's going to create the whole thing for you. And now you have a deployment where you can actually throw up, like, YSQL, which is NoSQL-like tables, Apache Cassandra compatible, and YSQL, which is Postgres compatible, and all of them running in this topology, right? Like geographically distributed and consistent. Right? So that's the real value. And obviously, if you think about transactional workloads, like Apache Cassandra doesn't have secondary indexes or a document data type. These are some of the things we can bring quickly. SQL doesn't have the notion of replication, fault tolerance, failover, data distribution across nodes. These are some of the things we can help. So I think we kind of make both sides more mature and easier to work with.
Okay, thank you very much. Very nice talk.
Yeah, thank you.
Okay, it looks like we are at the end of the hour. So maybe let's end with one last question. Anyone would like to ask this final question?
If
Okay,
nobody's asking, one quick
go ahead.
question, I guess. Faisal, if nobody's asking. So how big are you guys? How many people?
Company-wise, we're about 75, 80 people or so. So we're still pretty small.
And who's the main customers?
Main customers, like we have a number of Fortune 100s now, but Fortune 100 companies take a very, very, very long time in order to agree to put their name on the website. Some of them never do, but if you just go to our website success stories, you can see like Kroger is like one such large company that finally agreed to put it. But anyway, Kroger, Narvar, Plume, these are some of the companies I've seen inside for a bunch of guys. But there's a number of other bigger companies as well.
And you're venture funded, I'm assuming, right?
Our venture funded. We've raised a couple of rounds of funding, yes. And we're venture funded by Lightspeed Ventures and
I see.
Capital and IPC, some pretty brand name VCs.
So Sharad, are you thinking about quitting your day job? Is that what you're hearing?
Which area of the stack do you work on there? No, I'm kidding.
Yeah, wonderful. Well, great. Thank you so much. This was really fun.
Thanks a lot. This was great.
Thank you. Yes. There's no virtual clap. I guess there is a way to do that, right? So the action somehow or the other. There you go.
The words speak a lot. Thank you. Thank you, guys. Really appreciate it. Yeah.